Hi, so we're going to pick up the video here after we just did the calculation of frequency and given wavelength. And so that was the end of our introduction to how light behaves. A little bit about light. That was just a small introduction. Light can do, you could take a whole course on light, lots of courses on light. So that was just a very brief intro into it. Our goal in all this looking at light is now we're going to look at light and matter interacting. And our goal is to try to get to understand how scientists came up with electron configurations in orbitals and those kind of things that we have learned about. And so we're looking a little bit at the history and trying to understand a little bit better. So this is the video now is going to start talking about that. Some of the different scientists that were involved and some of the phenomenons they studied and some of their explanations that got us to the point that we are now. And so this is talking about here about Max Planck, and this is in section 7.2, and how he came up with quantized energy. So first, this is just an observation that not just that he had. He wasn't the first to have this observation. They had studied this for a while, and it's kind of something we see. And you might have never thought about it before, but many times a hot object or a hot material will give off light. It'll glow. So coals on the top there glow in a fire. Certain metal will turn red hot when you heat it to high temperature. So you see that heating element on an electric stove there. So when that heating element on that electric stove in the middle, when it's cool and just sitting there, it's black. And it's not giving off any light. But when you pass the electricity through it, it heats up, of course. We use that to boil our water and stuff. But it also turns red or yellow. It's giving off light. So you probably never thought about this before, but there's certain matter that when you put energy in, light comes out. So that's something that people wanted to study. If you have an incandescent light bulb, the one on the bottom there, the old type of light bulb that had a little filament in it, a little filament of wire. And when the electricity passes through that, the electricity we now know is flowing electrons. It heats up that little filament and it glows. And that's how we lit up our houses for many, many, many years. Now we have different types of light bulbs, a lot, but that was the first type we used. So the other observation, once scientists started looking at this on why this is happening, how this is happening, they just didn't want to know the why and the how. They wanted to know, they wanted to have mathematical equations that explain this. They wanted to be able to predict things. And turns out that the range of color that is emitted by an object changes as you increase its temperature. So first, the visible light that comes out is red. Okay, so if you heat something up it gets hot, we call it red hot. But eventually, the red will go to yellow and then maybe even white if something is white hot, like the bottom filament there. So that was another observation that they had. So, all right, so this sentence here says, classical theory did not mathematically explain the temperature dependence correctly. So we got to kind of talk about what that means. Around the time this was all happening, like 1900-ish, there already had been theories and mathematical equations to describe how light behaved, called Maxwell's theories. So you might know about Isaac Newton, and he did theories of motion. You might have studied that in physics already. So he has equations for motion like force and velocity and acceleration and things. Well, Maxwell did that for light. And so there was all these equations for them. And then those were the base equations, and then they could work with them and try to apply them to different situations. And so it's called classical theory, sort of like classic, I don't know, classic rock, right? That means kind of older rock music, right? So classical theory was the theory of the time before the modern theory came into effect. And so the theory that he was dealing with at the time, the mathematical part of it, wasn't matching up when they did the temperature dependence that we just talked about. They weren't getting the right predictions from it. And that was a problem, okay? So they didn't know what to quite do with it, because they have these theories. And remember, when something is a theory, that means it's been tested by many different means, and it's worked for many situations. So they have all these things that work great for light, these equations. But when they start to apply it to this problem, the problem of matter giving off light when it's heated, didn't work right. It did not give them what they expected to in terms of what type of wavelength was going to come out of the light, how much energy, etc., what type of light energy was coming out. So they were scientists were very perplexed. And Max Planck was the one who came in and explained this, or at least was able to help out explain it. And this happened in 1900. So what he said was that, well, when this energy is absorbed or released from atoms, because obviously these are atoms in this, let's say, metal filament that's glowing, or whatever they were using, when that's happening, he said, let's think about it that this energy that's going in, because the heat energy is going in and the light is coming out. So both of those are forms of energy. And he said, I think that when they're absorbed or released, there's certain small amounts that this happens in called quanta, that he called quanta. And furthermore, the energy of one quantum, so quantum is singular, quanta is plural. The energy of one quantum is equal to h, where h is a constant, times the frequency of the light that's coming out. So he was saying that the light that's coming out, the energy that's coming out of this matter, form of light, is not coming out is just a continuous stream of energy. It's actually like little chunks of energy. They're just so tiny that to us it looks like it's just a continuous stream of energy. An analogy to this, not the same thing, but analogy is sort of like if you see on a computer screen where it has pixels, and each of those pixels is the smallest piece of light that's coming out, but then altogether it makes up the whole screen. But there is a smallest amount that you have to get to, and you can't have the energy coming out any smaller, and that's the quantum. So the energy that's gained or lost by the atoms in this phenomenon is always a whole number multiple of the energy of one quantum. So the amount of energy, let's say, that's coming out of this glowing object is always E, and it's always equal to n times h nu, where n is 1, 2, 3, 4, 5, 6, 7. It's a whole number. It could be a 40 million or something, but it's a whole number. So the energy is coming out in little tiny bits, and you can't have energy less than one of these little tiny quantums, but it's always a whole number of those. So h is now named Planck's constant. He didn't call it that, but later on they named it after him. And it's 6.626 times 10 to the minus 34, and that is JS is joules seconds. So it's not joules, it's joules times seconds. And it's a very small number. So you see that one quantum is super small because it's got that 10 to the minus 34 on it. So it's very, very small, but it matters that it is a unit. It is one whole piece of energy. So a little piece of energy. So in other words, the energy is coming out in tiny little bits called quantum. Okay, and he was the first to use the concept of quantized energy. Before that, energy was thought of just like as a continuous smear of energy. There was no beginning or end. It was just like a continuous thing. And now he's saying, well, it looks that way, but they're really tiny little bits. Okay. All right, so here's a little picture that shows what happened when he did this. So let me get my pointer here. All right, so see this here where it says Rayleigh-Jean's law. Okay, so this dotted line here, okay, was what the classical theory is. Now, what are we graphing here? Well, on the x-axis, we have wavelength. It looks kind of weird to have it 1, 2, 3, 4, 5, 6, 7, but the units here are micrometers, not nanometers, all right? So over here, we have the very low wavelength. So down here, visible would still be like down here, okay? And in ultraviolet. Most of this is infrared. And then over here we have power. You can think of power as the amount of light that's coming out, like a brightness, how much light is coming out. So when you graph Planck's equation, so what did he do? Well, the equation is very complicated, but wherever there was energy, instead of just having energy, he put in this n times h frequency. So he included that quantized energy in little chunks. And when he graphed his equation, okay, he got this dark line. Now, the interesting part is the circles here, the actual circles, those are the data points. So they actually collected data, observations, where they measured the light that was coming out of these objects, and they measured the wavelength that was coming out. And so they have all these data points. So this dark line is not, it's not connecting the data points. That's the graph of his equation. You know, you graph a linear equation or whatever, that's his equation being graphed. The dotted line is what before Planck came along, how it graphed. That's why it bothered them, because see, their dotted line here did not match the data. And the data always rules in science. You have to be driven by the data. And so the data was telling them, hey, your equation's wrong, because if your equation was right, it would match up with the data. So what that did was start to convince them that Planck had to be right, that energy is not might seem like it's just any continuous amount. You can have any energy you want, but really it's very small quantized bits that just seems like it's continuous when you look at it, a lot of it. Okay, so our conclusions from Planck. Energy is quantized and can occur in discrete units of h times frequency. What he called a quantum is a packet of energy. And a system can transfer energy only in whole quanta. So meaning you can't have a half of one. So quanta, remember, is plural, quantum is singular. So you can have 1, 2, 3, 4, 5, 6 of them, but you can't have 1.5. The total energy transferred is always some whole number times h nu. H is this constant. You don't have to memorize it. I'll give it to you if you need it. So before he did this, scientists, it's sort of like you have this idea in your head, and they always had, besides just being scientists, they kind of had a philosophy about it. And their philosophy is about nature is in this Latin phrase here, which means nature does not make jumps. So when they looked at nature before this, so, you know, in the 1800s and earlier, to them it looked like everything was moving very smoothly. And when you think about it, it is. You know, the earth changes position and we get the seasons, the earth go around the sun, the earth goes around the sun and we have continuous seasons, the earth rotates and we get a day, we have, life has cycles to it. You know, people born and you grow and you die and then it starts over. And so there always seems to be this sort of continuous flow of things. And so that's what their idea of nature was, that it has a continuous flow. And so they thought that was like a very, everything was going smoothly up and down, back and forth around. And so, but what happened here is he said, well, it's not really like that in terms of energy transfer. It's actually making little jumps. It's actually has tiny little bits of energy. They just seem continuous because we're not looking that closely at them. So this was a change for them, but they had to accept it because it worked. The data, the equations worked. So Planck is the first to come up with the idea of quantized energy. Now, I know we talked about before that electrons have quantized energy. We're not there yet, okay? When Planck came up with the idea of quantized energy, electrons hadn't even been discovered yet. That doesn't even happen for like 5 more years. So he's not even looking at electrons now. There's not even thinking about electrons and protons. They don't know about how the atom looks. Rutherford hasn't done his experiment yet to show there's a nucleus. They're just looking at energy in, energy out, okay? So they're not thinking about electrons or anything like that yet. So in general, he's just saying that this energy is going into atoms and coming out of atoms in little tiny pieces. So that's where we're starting with. But he gets a lot of credit for that because that was a big jump. Okay, so the next thing we're going to talk about is another phenomenon that was studied around the same time, and that's something called the photoelectric effect. And in the photoelectric effect, what you do is you shine light of a certain wavelength, or you could say of a certain frequency, because they're related, right? One is, you calculate one from the other. So you shine light of a certain wavelength on a piece of metal. And if that wavelength is right, you might get electrons to come out of the metal. So at this point, they know about electrons. Okay, so we've jumped ahead in time a little bit. So turns out that each type of metal, so nickel or platinum or silver or iron, each type of metal has its own threshold frequency of light that will cause electrons to be ejected. If you use light that has a lower frequency than that threshold, nothing happens. The electrons don't come out, and it doesn't matter how bright the light is. So you could take a lower frequency of light and you could have it be really bright. We'll talk about that in a second, and nothing happens. Another way of saying it doesn't matter how bright the light is that it's independent of intensity. That's the same way of saying it doesn't matter how bright. Brightness and intensity is the same thing. So if you have a dimmer switch on a light and you turn it up, you're increasing the brightness of the light, or you could say you're increasing the intensity of the light. It means the same thing. So it didn't matter how bright that light was if you were at the wrong frequency. When you get to the threshold frequency, electrons start to be ejected from the metal. And we'll show you a picture of this in a minute. And then if you turn the brightness of that light up, so we're not changing the color of the light, we're not changing the frequency, we're just changing how bright it is. So imagine, and you turn up its green, it's still the same green, but it's just brighter, okay? When you do that, more electrons come out. All the electrons that come out they're moving at a certain speed or velocity, and they're all moving at the same speed, as long as you only are shining that one frequency of light on it. We'll look at a picture in a second. When you get above the threshold frequency, so you use different frequencies of light, electrons are ejected with higher velocity than at the threshold. So they come out. So as long as you're at the threshold or higher, the electrons come out, and now they're coming out faster, okay? And the same as when you're at the threshold frequency, if you turn the brightness of that light up, you get more electrons ejected. Okay, so that's a lot. Let's look at a picture here. So over here, we have a picture of, this says radiant energy. So that's light. See the little wave over here? So this is some metal surface. So the most basic thing is that in the photoelectric effect, light goes in and electrons come out. It has to be the right frequency of light. If it's the wrong frequency, this doesn't happen. This is a little bit more sophisticated, but this is like the original equipment, pretty close to what they used. They have the light coming onto this piece of metal. And they have the metal inside of this evacuated chamber. Evacuated means there's no air in it. And there's no air in it, so that when the electron comes off, it goes to this piece of metal here. And this piece of metal is attached to a battery, and it's positively charged. That's why the electrons go to it. That's why there's no air in here, because if there's air in here, the electrons will probably bump into the oxygen, and the oxygen likes electrons, so it will take it. This way, there's no oxygen in the way. So it just goes straight to this positive metal, or it could be even carbon rod here, positive rod. And then it goes into the battery and then goes through. And over here, this tells you that you have current flowing. So current is just the flow of electrons. So when this needle moves, it means the electrons are coming off, because once the electron comes off, they go all the way through and then through the circuit. And that's what your current is, the flow of electrons. So if this light is not the right frequency, then these electrons don't come off, and then this guy here would be, the needle wouldn't have moved. So that's the photoelectric effect picture. Okay, so what we find is that, or what Einstein came up with, is that light of a certain energy is needed to eject the electron from the metal atoms. So the frequency of the light and the energy of the light are related. Okay, so we're going to talk about that in a minute, because we know there was a threshold frequency. So now we're saying, well, that means it has a different energy. classical theory, there we are again. Classical theory, the theory of before they came up with all this new stuff around the turn of the last century, classical theory said that the velocity of the electrons that came off should increase when we increase the intensity, and we didn't observe that. So classical theory didn't work again. Now, it doesn't mean we have to throw all of classical theory out. It works for lots of different things. It's very important equations. It's just that in certain instances, we needed to modify things a bit because there were certain assumptions that were made. And so what was happening here is what was predicted is that when you increase the light intensity, that meant you were putting more energy in, which is true. If you turn up the dimmer switch and make the light brighter, it's more energy. So they said, well, that would mean that the electrons should come off faster because you're putting more energy in. The electrons should have more energy when they come off. And that didn't happen. They didn't have that observation. So something was wrong with their idea. What did happen is more electrons came off. So they didn't come off faster. They didn't have a higher speed, but you just got more of them coming off. So, and once you got above that threshold frequency, the excess light energy went and gave you faster electrons. So the way you got faster electrons wasn't by having brighter light, it was by having a different frequency of light. Okay, so Einstein is the one who explained this. So if you're a little confused, it took Einstein to explain this. So it's one of these things when we're in this chapter, when I do this face-to-face in class, we talk a lot about that, about how this stuff is hard. This stuff really was difficult for people at the time to understand. It's difficult. We're not showing you the equations exactly because they're kind of difficult. We're just trying to get you an idea of the different phenomenon that were studied and what they had to do to change their way of thinking in order to explain this. So if it's hard to understand, that's okay. It's one of those things you have to read about a few times, watch a few videos. I'll post some videos on it besides this one and see if you can understand it. So it's not something you can see once. If you're trying to go through this stuff once and understand it, it's not gonna happen. You gotta think about it for a while. So, and Einstein was the one who explained this. So yeah, it took a smart guy to do that. And it was in 1905. And what he said is that in order for me to explain what's going on in this phenomenon, in order for me to understand what's happening when the light hits the metal and the electron comes off, and not just why it happens, but why it happens in the way it does, what's with this threshold frequency, what's with this turning up the intensity business, etc. And he said, well, I can do that if I assume that light isn't just a wave, but it's also a particle. And light over the course of the centuries or so had been thought of in different ways. For a while, they thought it was a particle. And then they did some experiments and said, no, it's behaving like a wave. And that way kind of stuck, the wave way. And there was experiments that said, yeah, light is behaving like a wave. And so they had to stick with that because of those experiments. But now he's saying, well, can't throw out the fact that it's a wave because we know it behaves like a wave, but it also behaves like a particle. So we call that having duality, when something behaves in two different waves. So he said that, that light is composed of quantized packet of energy. We call those little packets of energy photons. He didn't call them that, and we came up with that later. They are sort of like particles of light, but they have no mass. So they're not like a particle like an atom is. And he said that the photon's energy, the little piece of light, this little packet of energy, he borrowed this from Planck. He said, yeah, Planck is right. What Planck was actually saying, this little quantized piece of energy that he had as his quanta, that is this little piece of light, and it's called we're going to call it now a photon. So that his energy, Planck's energy, is the energy of one photon of light. So the energy of the photon is equal to h times the frequency. And you should know that equation too. You don't have to memorize what the constant is. You don't have to memorize the h equals, well, I'll give you that, but you have to know, well, you have to know what this equation is. Okay, so you get two little equations you're supposed to know. So the energy of one little photon of light is equal to Planck's constant h times the frequency of that light. And if you think about it, there's two sides to this equation. Here, we're talking on this side here, we're talking about light as if it was a wave, because we're talking about its frequency, and that's a wave property. And here we're talking about light as if it was a particle, because we're saying the energy of the photon. So the energy of that packet or photon of light is related to its wave property. So it's got both parts to it. Okay, so let me get rid of this writing here for a second. Okay, the intensity of light. So imagine you have your dimmer switch on your light and it's really, really dim, and then you turn it up and now it's really, really bright. That intensity comes from the number of photons present, not their individual energy. So imagine your dimmer switch is hooked up to a green light, not a white light like a normal light in your kitchen or something like that, but just let's say you have a green bulb in there, and it's really, really dim. Now turn it up and now it becomes brighter and brighter and brighter. It's the same color of light. It hasn't changed, and that means color corresponds to wavelength and frequency. So you haven't changed the wavelength, you haven't changed the frequency. So what you've done is increase the number of photons that are coming out with that frequency. So each photon that's coming out of your green light has, oops, hold on, I'm trying to get the pen here. Pen. Each photon that's coming out of your green light has the same frequency. So it has the same energy, okay? So each one has the same. But when you increase the intensity, you're just putting more of them out. So they're all little packets of energy, and now you're just throwing more of them, okay? So back to the photoelectric effect. So if you go over here and look at the picture up in the top corner here, these things here, okay, these little squiggles, those are just a cartoon representation of a photon. Doesn't mean it looks like that. That's just our way of showing it in this picture. So this says we have some sodium metal, not sodium plus 1, sodium that is still 0. Okay, and so all these photons are hitting this metal. Every single photon is identical. That's because they all have the same frequency. So what's going to happen is every photon is going to hit a different atom. So this photon that I circled hits an atom. This photon hits a different atom. This photon hits a different atom, okay? And when that photon hits the atom, it has enough, the energy of the photon is enough to kick an electron off. So that's that electron. This photon hits an sodium atom and it kicks an electron off, etc. So that's what's happening here. This photon hit an atom and it kicks this electron off. So a metal atom absorbs a photon of light, and the photon's energy is absorbed by the electron, and that gives it enough energy to escape the atom. So every photon gets absorbed by one atom. So one photon, one atom, one electron. So by doing this, he was able to explain all the parts of the photoelectric effect, because he was able to explain why there had to be a threshold frequency. Because if your frequency is too low, then your energy is too low. Because see frequency here, right? Frequency is related to energy. Higher the frequency, the higher the energy. So if your frequency was below the threshold, there wasn't enough energy. And what would happen is the atom would either not absorb it, or if it did absorb it, it didn't have enough energy to release an electron. So you got to get to that point where it has enough energy to kick the electron out. Then if you increase the intensity of the light, basically that just means you're shooting more photons at it. All the photons have the same energy, so more photons mean more electrons coming off. But they're all coming off at the same speed. Okay. All right. So Einstein won the Nobel Prize for this. He did not win the Nobel Prize for E equals mc squared, which we've probably all heard of. He won the Nobel Prize for explaining the photoelectric effect and coming up with the idea of photons. And so it's kind of a confusing thing and hard to understand. How can something be a wave and a particle? How can it have no mass? etc. So I always throw this slide in here. On the right, you see that little squiggle. That's just a diagram of the photoelectric effect. You got the photon coming in, the electron coming off. And of course, when the electron comes off atom, it's now an ion. It's lost an electron. So that's why it says photoion down there. But I put it on there for this. This is something that Einstein apparently wrote in a letter. He didn't write it in English, so this is the translation. So it says, so he wrote it in 1951. So this is about almost 50 years after he came up with the idea of photons. And he says, all these 50 years of conscious brooding have brought me no nearer to the answer to the question, what are light quanta? So, okay, light quanta are photons. He didn't call them photons. He called them light quanta. We just call them photons. So he basically, this says, for 50 years, he thought about it. What is a photon? What actually is it? And he still didn't figure it out. It took 50 years, he still didn't understand it. He says, nowadays, every rascal thinks he knows, but he's mistaken. So he said, Einstein thought about it for 50 years and still didn't quite grasp it. He could do the math of it. He could use it to explain something, but actually grasp what it all meant, he didn't. So if you're a little confused, you know, Einstein had 50 years and still didn't quite figure it out. So keep thinking. Okay. So what we're going to look at now we have another equation. And it's the energy of a photon equation. The energy of a photon of light is proportional to its frequency. The higher the frequency, the higher the energy. And we know that frequency and wavelength are inversely proportional. So therefore, longer wavelength is lower energy. So I'm going to show you that in a second. I'm going to write out the equation in a second. But for right now, if you look at the waves to the right, get my pointer out here. So if you look at those waves on the right-hand side of the screen, we've got this one down here. This is very high frequency light. You can see as these would go past you, a lot of them would go past you in a second. High frequency, low, small wavelength. Then this would be a longer wavelength here, but a lower frequency, because remember those are, and this is sort of in the middle. These are, so it's inversely proportional. So the longer the wavelength, here's the longer the wavelength, the lower the energy. This would be a higher energy light. So, and that's based on what we know of the equation. Okay, so which light is higher in energy, blue or red? Well, we just got through saying this blue light here, because remember, blue light has energies that are shorter than red. I'm sorry, take that back, start again. It has wavelengths that are shorter than red. So red has longer wavelengths, so therefore lower energy. We'll write out the equations in a second. Okay, so here is a picture of the photoelectric effect happening, and it's kind of an interesting picture. I like this one because it puts everything together. First of all, it's using down here a different unit of energy than we're used to. We're used to joules, but these energies that we're talking about of photons, of single photons, the energy of the electron when it comes off are really tiny. These are tiny little particles. So using joules are kind of big for that. So they have this number of electron. This EV is called an electron volt. You don't have to know this. I'm not going to work in electron volts, but I just wanted to explain it. So it's just a unit of energy, 1.6 times 10 to the minus 19 joules. So 1 electron volt is a unit of energy equal to this many joules. Okay, so in this case, it says here that this metal is potassium. And on potassium, the amount of energy it needs to eject, I'm sorry, the electron, the minimum you need, the minimum amount of energy that that photon needs is 2 electron volts. Okay, so that's our threshold energy. So remember, let's write this out here. Couple things. We learned before that c, speed of light, equals lambda, the wavelength, times nu, the frequency. We just learned that the energy of a photon, pH, energy of a photon, is equal to Planck's constant, which is h, times the frequency. Okay. I can combine these equations. I can solve the top one here. If I take the top one and I solve for frequency, I get frequency equals C over lambda. And now I can take this C over lambda and I can replace the frequency down here. You don't have to do this, but it's a really helpful thing to do. And then we find out the energy of a photon in terms of its wavelength. So energy of a photon would then be equal to, the H is still there, so H, and then instead of this frequency here, I'm going to write C over lambda. So HC over lambda. So the energy of a photon can be also written as HC over lambda. H and C are both constants, so just plop those in there. So we see here what we said on the last slide is that the energy of the light, the energy of the photon of light, is inversely related to its wavelength. So the bigger that number on the bottom, the smaller the energy, and vice versa. So if we look over here, okay, this says 700 nanometer light. That's red light. 700 would be in red, in the red range. That light, each photon of that light is 1.77 electron volts. Where'd they get that from? Well, they use this equation. They found H, H is a constant, so they put that in there. They put C in there, and they put their 700 nanometers in there. That gave them an energy. That energy is going to come out in joules because H has units of joules on it. And then they use this guy here, which you don't have to memorize, but that's what they used to convert it to electron volts. So it's really just 2 steps. And so that's, using that, that's 1.77 electron volts. This green light, which is 550 nanometers, is 2.25 electron volts. And this violet light over here with 400 nanometers is 3.1 electron volts. So what happens is the potassium needs 2 electron volts to eject the electron. So the red light doesn't have enough energy at 1.77 electron volts per photon. That's each photon. So hits it, nothing happens. Excuse me. The green light has 2.25 electron volts. So it's got more than enough, a little bit more than enough. So when it hits, the electron comes off. I'm going to switch to my laser pointer here. So when this green photon hits the an atom, the electron comes out, and then this is how fast it comes out, at around 3 times 10 to the 5th meters per second. When the violet light hits it, it's got more energy in each photon. So there's like 1.1 extra electron volts there. And that means the electron comes off faster at around 6 times 10 to the 5th meters per second. So this is an example of showing you the threshold frequency needs to be around this green light that has enough higher enough frequency. But the reason there is a threshold frequency is because it's really a threshold energy. The energy of the photon is what's important. We call it a threshold frequency here, nu, but it's because the energy of the photon comes from that frequency. I'm not going to go over this. You can look at it if you want to. It's in the PowerPoint posted. This just kind of does a little, it's kind of interesting. Does a little history of how people thought of light as a wave, and then as a particle, and then as a wave, and then as a particle, and then back to, and finally to Einstein's words, both. And that's what he won the Nobel Prize for. You could take a look at that if you find it interesting. Don't worry, I won't quiz you on that. All right, so we're going to do a little math here. So calculate the energy of 1 mole of photons of red light that have a frequency of 4.29 times 10 to the 14 inverse seconds. So remember, the energy of each photon is given from our equation, but if you have a whole bunch of photons, then you can add all their energy up and have the total energy, okay? So that's what we're going to do here. So this equation, it's not really an equation that you're going to find in a book. It's just common sense, this E total equation. So let me get my pen back. So what it tells us is that since photons are little bits of energy, each little bit of energy, if you look at the total energy that's, let's say, hitting you. So let's say you're sitting under a light and all these photons are streaming on you. The total amount of energy that's hitting you is going to be equal to the number of photons, I'm sorry, the energy of one little photon. So that's what this is, the energy of just one little photon times the number of photons that actually hit you. Makes sense, right? So that's what we're going to do. So the energy, if you have a whole mole of photons, okay. So we know the energy of one photon is given by this equation here. H times the frequency is the energy of one photon. And that's what this calculation tells us. So here's H, 6.626 times 10 to the minus 34 joules times seconds, times the frequency that was given in the problem. So that's what this is. So we just took the frequency that was given up here and we multiplied by the constant, which would be given to you for H. Do that, come out with that each photon, that's what this is, the energy of the photon is equal to 2.84 times 10 to the minus 19 joules. And I just wrote per photon after it to remind you that that's just the energy of one tiny little photon. But they want to know the total energy of if you have a mole of those photons. Well, remember, a mole is Avogadro's number. So if we take the energy of one photon, which I've written here as joules per photon, and we multiply it by Avogadro's number, which is the number of photons in a mole. So Avogadro's number just tells us how many particles are in a mole. In this case, the particles are photons. You can have moles of photons. It's just a way to count them. So we're just going to multiply those two. And I also did this little thing down here. Let me erase for a second. Make this clear here. Okay. So this next step, which I just did on the bottom here, that it says this kilojoules and joules. That's because I wanted to change my answer to kilojoules, because if I do this, my answer is going to come out in joules, and it's going to be a pretty big number. So I decided to then change it to kilojoules. You wouldn't have to do this unless you were told to, but I decided to do it. And it comes out to 171 kilojoules per mole of photons. So that's the energy if the entire mole of photons were to be calculated. So this top equation here is something, like I said, it's not really an equation you're going to find, it's just common sense, is that the energy total is equal to the energy of each photon times the number of photons. Okay, so we're going to do another example of this. And that is the total light energy released by a source is 57 kilojoules over a 2-hour period. If the wavelength released is 351 nanometers, how many photons are released in that 2-hour period? Okay, and then we're going to do another one that says a watt is a unit of power, and we'll get to that next. Okay, so answers in the packet, and this we're going to do this on, it says done on the board if time allows. I'm going to actually do this for you in a different video, so we're going to pick this up in the next video. So I'm going to turn this one off for now.